Understanding combustion through images. You will see several illustrative films on gas, liquid and solid combustion processes. Flames that arise from an initial premixing of fuel and gas are called premix flames. Flames where mixing occurs at the flame are called diffusion flames. And combustion acoustics is due to the coupling between heat released by combustion and acoustic waves generated in the medium. About 70% of the videos are from experiments conducted in the laboratory, rest is from public domain. This needs a one-sided open tube with an arrangement for filling the tube with the gaseous mixture of known composition and sparking at the top. Note that the stoichiometric flames are faster than lean or rich mixtures. Rich mixtures have actually cellular structures. The flame speed is representative of the reactivity of the fuel-air mixture. The steady combustion of the flow of premixed mixture through a Bunsen burner shows a flame that becomes more intensely turbulent till it cannot sustain. It actually blows off then. Just lift and then they blow off. Steady combustion, flashback and blow off when the flow of premixed gases is decreased slowly through tubes of different diameters. The flame blows off in the smallest diameter tubes since the quench distance of the mixture is comparable to the diameter of the tube. It flashes back in the other three tubes. At the same power level, the premix flame volume is about half of a diffusion flame and hence the heat release rate of a premix flame is higher accordingly. Premix flames have a higher heat release rate because fuel and oxidizer are initially well mixed. A fire wheel is a combination of concentrated heat source coupled with organized source of angular momentum, either from wind shear or from fire's convection column, that must help create large swirl velocities as air is entrained into the fire plume. In the laboratory experiments, fans can be arranged to provide swirling flows. Or a rotating table with meshed cylindrical structure providing a source of angular momentum can be used. The ultra-high speed film shows the pressure variation caused by the combustion in a four-stroke engine. The movement of the cylinder is clearly visible, as is the flame front of the combustion around the spark plug. The ultra-high-speed film shows the combustion structure inside the cylinder as a Schlieren picture. Schlieren photography picks out the density gradients inside the flow. Note the complex turbulent flame propagation inside the combustion space of the cylinder. Diffusion flame with increased flow from burner stabilized mode to lift and blow off. Diffusion flame is obtained by causing the flow of a fuel, in this case LPG, through the Bunsen burner. Air for the combustion enters by diffusion. As the flow rate is increased, the flame height increases nearly linearly. It also lifts off from the edge of the tube. The height then levels off with the flow becoming turbulent. The jet entrains air from outside, and beyond some flow rate, the flame acquires partly premixed character. With increased flow rate, the flame blows off. Normally, fuel jet and air or oxidizers surround each other. This leads to combustion with visible flame. By arranging the fuel and oxidizer jets at a distance from each other and making the jet speeds high, of the order of 100 to 300 meters per second, the jets entrain the high temperature products of combustion to dilute the fuel and oxygen fraction with increased temperature of the jets. Reaction begins at high temperature, typically 1000 degrees centigrade or more, and the combustion process will occur in a mode close to stirred reactor. Such a combustion process will be non-sooty and the flame will be near transparent. Hence the name flameless combustion mode. The high-speed jets on the right are for flameless combustion. Gas hydrates are methane enclosed in a crystalline cage of water molecules formed deep under the sea, implying very high pressures. As you see in the last picture, methane burns with ice slowly melting away. It is the water present on the palm that lets it be held on the palm. In this experiment, we observe that the flame is a conductor of electricity. The flame is a conductor of electricity since it is composed of charged particles, ions and electrons. High voltage of 1.1 kilovolts is established between two electrodes with sharp ends. When the flame is brought such that it covers the fine ends of the electrodes, the circuit gets closed, current flows and the bulb glows red. When the flame is drawn away, the circuit is open. Droplet combustion is an important process that occurs in burners, reciprocating engines and gas turbines. This is captured by burning the droplets on a quartz fiber at normal gravity. You will see the following droplets being burned: ethanol, gasoline, kerosene and diesel. Ignition is by electrical spark, and the red dot on the plot shows the path of the square of the droplet diameter with time. Note the near transparency of the ethanol flame. A composite picture of the droplet combustion process. It takes about 2.5 seconds to burn the 2.5 millimeter droplet. We move on to spray combustion in practical systems, namely reciprocating engines, gas turbines, and rocket engines. Liquid is always introduced into a combustion system in terms of fine droplets by atomizing them in injectors. The jet diameters are typically 20 to 50 microns. Notice the periodic injection of diesel in diesel engines. The liquid spray combustion in gas turbines is continuous. Notice the fine spray in a rocket engine injector head due to impinging jets. The burn time of fine droplets is in terms of fractions of milliseconds in actual systems. Hypergolicity is a property of a specific combination of fuels and oxidizers in which as soon as they come into contact with each other, they react vigorously and lead to a flame in the gas phase. In this experiment, nitrogen tetroxide is the oxidizer and aniline is used as the fuel. Nitrogen tetroxide has a boiling point of 21 degrees centigrade and is usually stored under pressure. Nitrogen tetroxide is put into the test tube and aniline is dropped from a pipette. The flame appears within 2 to 5 milliseconds. These propellants are used in rocket engines. Two control rockets based on nitrogen tetroxide and monomethyl hydrazine are being fired here in a test bed. Combustion of wood and any biomass occurs in two steps, flaming combustion and char oxidation. The former occurs in the gas phase and the latter occurs on the surface. Ignition of wood needs a flame to heat up the material till the volatiles are released and a gaseous flame is initiated. Combustion of a wood sphere in air is shown here. The sphere is ignited with a naked flame. After ignition, the sustained combustion occurs because the flame transfers heat to the surface to generate the volatiles that burn in the gas phase. Char oxidation occurs by diffusive transport of oxygen to the surface from the gas phase. Both these are diffusion controlled. Volatile combustion occurs faster than char oxidation. A comparison of the combustion of wood sphere in air and oxygen as the oxidants is shown here. The flame is brighter with oxygen and the wood sphere burns faster and fragments as well because of the sharp heating of the solid. The total combustion time of wood sphere with oxygen is about 16 seconds, whereas the flaming time of wood sphere with air is 20 seconds and the total burn time is 85 seconds. We now look at top-lit reverse downdraft gasifier with wood chips and fine biomass as fuels. We also look at actual modern domestic biomass pellet stove. Gasification is a process by which solid or liquid fuel thermally reacting with an oxidizer generates a combustible gas. What you see here is a reverse downdraft gasifier with solid fuel pieces packed into a container from the bottom of which is passed air. Ignition is performed by spraying kerosene on the top layer and lighting the kerosene. The gases generated burn with atmospheric air. In the char mode, the gases are generated at the bottom region and the gases are burnt above it. Note the fine biomass pellet stove functioning here. You can see the hot surface of the combusting fuel. We look at practical gasifier stove. The gasification air comes from the bottom and the combustion air comes from the sides at the top. Look at the outstanding quality of combustion here. Solid propellants are a mix of solid oxidizer like ammonium perchlorate and fuel, aluminum powder, at high solid loading in a binder matrix of a fuel like HDPB or others. A model of solid propellant is the sandwich propellant. The burn rate of a model sandwich propellant is examined at low pressures. These burn rates vary from 1 to 2 millimeters per second. Solid propellant combustion does not need an external oxidizer. A piece of double-base propellant is placed such that it is surrounded by nitrogen. You can see the matchstick flame is extinguished in the nitrogen stream. The propellant is electrically ignited here using an nichrome wire. The propellant burns at about 2.5 millimeters per second. Solid propellants are designed to burn at very high pressures. They are tested in what are known as strand burners. You will see the propellant burning at 10 and 70 atmospheres at 5 and 17 millimeters per second respectively. A large solid rocket motor on a test tank. It burns every second about half a ton of the propellant to produce 1 meganewton of thrust for about 94 seconds. Hybrid rockets are the safest form of rockets. They use a liquid or gaseous oxidizer and a solid fuel. In the demonstration shown here, a gaseous oxidizer, namely oxygen, and a solid polymeric fuel are used. The rocket motor startup uses an electrically operated pyrotechnic that causes sustained solid propellant burning for a few seconds. Demonstration of a rocket-based human flight.
That's a timer. That's hooked to a buzzer in the back of the helmet here, and we set this for the flight duration. And then when you're halfway through the flight, you get one buzz each second for 5 seconds.
This is to warn you.
Right.
How long does it last up there?
21.5 seconds.
So if you make a mistake, if you don't hear the buzz, you're really in for it.
Well, you can't miss it. You don't actually hear it, you feel it. It's a vibrator that presses against your skull.
If anything should go wrong, how do you get down? I mean, is there a parachute harness of any kind?
No, we rely on gravity.
Richter tube is a tube that converts heat applied in specific locations to sound by creating a self-amplified standing wave. The thermoacoustic interaction is governed by Rayleigh's criterion, which states that the energy introduced into the fluctuating pressure wave must be broadly in phase for the oscillation to amplify. In this experiment with 50 cm long tube, a few pieces of charcoal set on a wire guard at about quarter of the height of the tube is brought to a red hot condition with a Bunsen flame. When this flame is withdrawn, the tube starts singing at a frequency, and this frequency can be simply calculated for an open tube as the acoustic speed divided by twice the tube length. A similar experiment with a longer tube. An example of unsteady or pulse combustion can be seen in a bottle with liquid fuel. In the bottle, with the fuel is initially shaken, placed and lit on the top, combustion proceeds in an unsteady mode. Rubin's tube is an example of unsteady combustion. The diffusion flames out of a large number of holes of the tube dance to the acoustic modes generated by the speaker fed with the sound. The fuel gas, which is LPG here, is supplied into the tubes from the other end. The standing pressure waves that change with time in the tube lead to the variation in flow rates from the tubes.